So we are at last in a position to link the ideal gas law with Newton's second law of motion. Now, I could do this by taking Newton's second law of motion, getting all the way to PV equals nRT. But what I'm going to choose to do instead, because I think it's conceptually a little more transparent, is I'm going to link the two of them together through the RMS speed. So I will work on finding the RMS speed of a molecule and then tie that into the ideal gas law. So with that, I'm going to start by thinking about a box that's length L on a side. And at the moment, it is the most boring gas-filled box you can imagine. It has one molecule in it, mass M. Okay, so clearly this is going to satisfy being an ideal gas because it can only interact with the walls of the container. We'll extend this to thinking about N molecules pretty quick. And as far as vessels that are other shapes, I'll just assert there are dirty math tricks you can use once you've proven it for a cube. You can then basically make collections of cubes that converge to whatever shape it is you actually want. That part I'm going to just have you take on faith. Anyway, so here it is. It's going at some initial velocity, and it's going to go until it hits the wall of the container right there, and it's going to bounce back out, and now it's heading off at some final velocity. Still that same mass M. So here, this is an elastic collision with the wall, and so we know that since the motion was in x, there was no change in the y or the z components of velocity. So we're only thinking about the x component at the moment. So we can think about the impulse that in the x direction that the wall exerted on the molecule. And by the impulse momentum theorem, that will be equal to the change in the x component of the momentum. Well, since it was mv sub x to the right and then became minus mv sub x because we came to the left, the change in the momentum is going to be minus 2mvx. Okay. Now, by Newton's third law, that means that the molecule exerted an equal and opposite impulse on the wall. So that'll be plus 2mvx. And that would also be how we would be attempting to change the x component momentum of the wall. Now, there are other forces in place keeping the wall from moving, but if the wall didn't have anything attached to it, that is what we would be changing the momentum to. All right. Now, what I want to do is I want to characterize the average force that this molecule is exerting on this wall. And so the idea is we can think about it as it keeps rattling back and forth. Sure, it'll hit the other walls, and we'll deal with the fact that it's hitting the other walls in a second, but it won't matter as far as the x is concerned, because the interactions in y and z are just in y and z, and we're only changing, and so for x, we're only changing the x component momentum. All right. So if we think about this wall, what it means is that in x, this is just rattling back and forth. Constant speed changes its velocity every half of a round trip from plus to minus. That's it in the x direction. So we can figure out the round trip time. So the round trip distance would be 2L, and that would be equal to the x component of the velocity times our round trip time. So we can rewrite that to say that our round trip time is 2L over v sub x. Okay, So now with that, we can characterize the average force that that right-hand wall is feeling. Again, it's just in the x direction, so we're just taking an x component. So this would be the change in its x component momentum over the time. Now, again, this is if there was nothing holding this wall in place. Obviously, there are forces holding the wall in place. But that doesn't change what the force is. So we can put in what our change in momentum was. It's 2 mv sub x. And we can put in our round trip time. There'll be 2L over v sub x. All right, so first small favor is the 2's cancel. That's good. And then we can rearrange this and get mv sub x squared over L. And almost immediately we should be starting to have alarm bells going off, because this looks for all the world like a kinetic energy. In fact, it's 2 times the kinetic energy. Well, it would be 2 times the kinetic energy, except that it's just an x component. If this were a speed, instead of just the square of the x component, it would be a kinetic energy. So it's not yet, but maybe we can make it, massage it towards 1, and that's going to be how we link into temperature. Now, by definition of pressure, this force is going to be equal to the pressure that the gas is exerting on the wall, my whole mighty 1 molecule of gas, times L squared. Now, realistically, we have more than 1 molecule. So now at this point, we're going to say we have capital N molecules. Nothing changed for the analysis for 1 molecule versus n molecules, except that now we will have n times as many collisions. And what I'm going to need here is going to be the average value of Vx squared in order to properly characterize the force. So I can rearrange this and get that the pressure is Nm over L cubed times the average value of Vx squared. And this bar over the top just means that I'm taking an average. And since it's including the square, this is the average value of Vx squared, which is not the same thing as the square of the average value of Vx. So remember, the average value of Vx is 0. Half the time the particles are going to the right, half the time they're going to the left. All right. But this L cubed here, that's just the volume of my vessel. So I can rewrite this again to say that it's the number density times mv sub x squared bar. So the average value of Vx squared, which is not the same as the square of the average value of Vx. And here, I'll assert that this works for a general shape. The argument is annoyingly elaborate, but the basic idea is you can just create a whole bunch of these cubes and stack them all together, and you can eventually make sufficiently tiny cubes that the arrangement of cubes basically looks like a Lego figure of whatever you want, and then you make your Legos as small as possible. It's an annoying argument, and you get the same result at the end. So, like I said, I'd like to get this into a kinetic energy-ish kind of thing. If I could just get rid of this sub x, I would be really happy. Well, it turns out I can. And that is because of isotropy. So that's a fancy word. And what does that mean? So what it means is that there was absolutely nothing about this argument that was special to the x direction. We could have used this to analyze how it's rattling in y or in z just as well. So since there's absolutely nothing different about x, y, and z other than just we had to call them x, y, and z, the average value of Vx squared has to be the same as the average value of Vy squared, and it has to be the same as the average value of Vz squared. Because if it wasn't, then there'd be a special direction, and nature doesn't care which way we point our axes, because coordinate axes are an invention of humanity. But here's where we can finally start to get rid of the subscripts. And this is that we can also relate these to the square of the average speed via the Pythagorean theorem. So the Pythagorean theorem would say that v squared is equal to vx squared plus vy squared plus vz squared. Now, this is true for a particular molecule, and it's true for the average value of all of the molecules. So this is the average of, if I take vx squared and add to that vy squared and add to that vz squared and then take an average of that over all the molecules, that's what that is. However, in this particular case, we can go ahead and observe that since this is squares, these are all positive numbers. And so in this particular case, the average value of the sum is the same as the sum of the average values. This wouldn't be true if, say, this could be negative, if one of these could be negative. But since they're all squared, they're all forced to be positive. And so in this case, the average value of this sum of squares is equal to the sum of the average values of each of the squares individually. Now we're getting somewhere. By isotropy, all three of these are the same. So I can just say vy squared bar is equal to vx squared bar, and vz squared bar is equal to vx squared bar. So that's going to give me 3 vx squared bar. All right, so now I can just divide through by 3 on both sides and get that the average value of vx squared bar is 1/3 the average of the square of the speed. All right, so going back to here, let's just call this star for a moment here. So we were at the point where we said that the pressure was equal to the number density times the mass times the average value of Vx squared. But the average value of Vx squared is not 1/2, 1/3, is 1/3 of the average value of the square of the speed. So we're going to put that in. So now I can write that PV equals, P equals N M over 3V, capital V here, little Vx squared bar. Whoops, sorry, no x there because I substituted in for it. My bad. All right. So now I can times both sides through by V and get the ideal gas law. So this is where I'm going to be linking it. PV equals, well, we have N mv squared bar over 3, right? But the ideal gas law also says that has to be equal to N times Boltzmann's constant times T. Now here is where what's really going on is Boltzmann has now identified that the temperature is proportional to the average kinetic energy of the molecule. And so he's made this identification. And this is why we can make this equality. So he's observing that KT is mv squared bar over 3. And we'll justify that a bit when we get back into thinking about heat transfer a bit more and connecting back to the Zeroth Law of Thermodynamics. But for the moment, we can say this equals this. That will let me rearrange, equating these two, to get the average value of v squared is 3kt over m. Now, if I take the square root of both sides, that is the square root of the mean of the square. So that's VRMS. So this is the square root of 3kt over the mass of the particle. Now I can put back in to here for the pressure. So I can rewrite this as pressure is N over V times M VRMS squared over 3. So again, this MVRMS squared is looking awful energy-ish. And so now we can see that the pressure is related to the energy density of the particles. All right, so on that note, let's figure out what the average energy of my particle is. So this is a lowercase Greek epsilon. It is one of the letters, it's the letter used for E. And we're going to be using it for our thermal energy for one particle. In this case, it's nothing but being just the average kinetic energy of a particle. So I'll just say K bar just for the moment here. That's 1/2 m v squared bar, because again, we're taking averages. But from here, this bit right here, v squared bar is 3kt over m. So this is going to be getting 1/2 m 3k t over m. I can cancel the m's and be left with 3/2 kt. So the thermal energy of the entire gas will be n molecules times the thermal energy of a particular of the average thermal energy of a molecule. So this will be 3/2 n kt. So the thermal energy of an ideal gas is 3/2 n kt, and that's telling us what the that's n times the average kinetic energy of one molecule. Now, because it's an ideal gas, we're thinking about non-interacting tiny billiard balls, so there's no potential energy to worry about. That's going to give us a quirk that we'll have to think about in the next video, but we'll hold off on that for the moment. But just to help make this a little bit more concrete, let's figure out what is the average thermal energy of an argon atom. At 300 Kelvin, which is a room-ish temperature. And while we're at it, we'd also like to know, what is the RMS speed? Remember, once we have the RMS speed, if we wanted the average speed or the most probable speed, we'd just take 92 or 82% of that number. So this is the easiest of the numbers to calculate for that. Well, we have that the thermal energy of a particle is 3/2 kt, and it doesn't matter what the particle is. So it could be uranium, a lot heavier than argon. It could be hydrogen, a lot less. The average kinetic energy of that particle will be the same. Obviously, for a lighter particle, its speed will be higher, and for a heavier particle, its speed will be lower. So this will be 3/2. Boltzmann's constant is 1.38 times 10 to the negative 23rd joules per Kelvin. And our temperature is 300 Kelvin. And this is a case where we have to work in absolute temperature. So if you're given a Celsius temperature, you're going to have to add 273.15 to it. So we get that the average kinetic energy of an argon molecule at 300 Kelvin is 6.31 times 10 to the negative 21 joules. And that's also the average kinetic energy of any, if we had a mix of gases, say it was air, as long as we could approximate the air as an ideal gas, that would also be the average kinetic energy of any other noble gas in the mix, or because again, I have to sweep under the rug some issues with molecules at the moment. That will be coming next video. All right. Now, how about getting our RMS speed? Well, the average thermal energy will be 1/2 m VRMS squared. So VRMS squared is going to be 2 times the thermal energy of a molecule that we just found over its mass. Or VRMS is the square root of that. All right. So we can plug those in. So we just found from here that the average thermal energy of an argon molecule at 300 Kelvin is 6.31 times 10 to the negative 21 joules. And you can look up that the mass of an argon atom is 6.63 times 10 to the negative 26 kilograms, to give you 433 meters per second, which speed of sound is usually considered to be, at those temperatures, is in the 340-ish meters per second range. So this seems like a perfectly reasonable number to be getting. All right, so I want to revisit heat transfer and the Zeroth law for just a moment. So let's go back to how we were thinking about how heat got transferred. In the example I did when I first introduced the Zeroth law, I talked about a salt crystal. But here, since we've been talking about gases, what we can imagine, this is the usual way you do it, is you imagine a super duper thin wall. I usually call it a membrane. So we'll have a collection of gas here at some temperature T1 initial. And we'll have some more gas over here at T2 initial. And what we can imagine happening is let's say this one, that T1 initial is hotter than T2 initial. We know that we're going to have a heat transfer from the hot thing to the cold thing. So what we can imagine here is, on average, this molecule is going to be fast. And it's going to collide here with some molecule that's slow. So every so often, these two will just perfectly meet at this membrane. The membrane only exists for us to conceptually not mix the gas. However, the analysis turns out to be exactly the same if we get rid of the membrane and just let the gas molecules mix. But conceptually, we can imagine this here just so that we don't have the mixing happening and it's easier to see. So what will happen is we'll have an elastic collision here. And so then the molecule that was faster will be going slower, and the molecule that was slower will be going faster. So this one will have lost energy. This one will have gained energy. So this whole process will come to a stop. So we'll have equilibrium when there's no net exchange of energy between collisions anymore. So this means that when the average value of a molecule on the left side of the container equals the average temperature of a molecule on the right side of the container. But we just saw that for an ideal gas, the thermal energy is 3/2 kT for a molecule. So this will mean that T1 final equals T2 final equals our T final. And what we'll have here is that T1 final will be T final will be between T1 initial and T2 initial. So here we're just doing this for a gas, so we don't have to think about phase changes. All the phase changes do is just make the analysis a little more tedious, but it's still exactly the same idea. We will continue to have collisions until the average energy of each individual molecule from what was the hotter sample is equal to the average energy of each molecule in what was the colder sample. And at that point, there is no longer an exchange of thermal energy. So this will mean that the two things are in thermal equilibrium and have the same temperature via the Zeroth law. Now, I mentioned that earlier that Boltzmann had identified that the temperature was proportional to the thermal energy, right? What I've been sweeping under the rug is this 3/2 business. So far we have for an ideal gas, that's 3/2 kT. With real-world gases, we'll see in the next video that sometimes this coefficient is something other than 3/2, but I just want to say for now, and I'll say more in the next video, that this is actually how we define temperature now with the SI revisions that occurred in 2018. It is defined by making Boltzmann's constant an exact number. So I'll get into how to deal with this 3/2 and the fact that it can be equal to something else in certain circumstances in the next video. So we'll see you over there.